Good afternoon, everyone, or good morning, depending on zone. Welcome to the invited talk by Dr. Kleanthis Nicolaides with topic The Science of Meteorology and Remote Sensing Applications. We will start with a short welcome note by Professor Fedon Kyriakidis, and we will then proceed to the talk. The talk will be recorded, so please turn off your cameras and microphones. We will allow questions only through the chat, and they will be answered after the talk. At this point, I would like to invite the research coordinator of the ERATOSTHENES Centre of Excellence, Professor Fedon Kyriakidis, for a welcome note.
Director of the Department of Meteorology of Cyprus.
We cannot hear you very well, actually.
Hear me now?
Yes, better.
So I would like to extend a warm welcome to Dr. Kleanthis Nicolaides, the Director of the Department of Meteorology of Cyprus. It is a great pleasure to have him here for this event, which is one of the events during a series of virtual meetings due to the pandemic, during which the Center of Excellence public and bring together researchers on different topics by inviting key people in Cyprus for topics that are in the agenda and the
Now we lost you again. If you could please stay close to the microphone.
The microphone is here, so let me.
Yeah.
Where was I? Okay, let's go on.
Okay, thank you. Dr. Nicolaides' present status is that of the Director of the Department of Meteorology of Cyprus since August 2016, while he was employed by the department since February 1988. He owns a Bachelor of Science degree in Physics from the School of Physics and Mathematics, Aristotelian University of Thessaloniki, Greece, a PhD degree on meteorology with a thesis on Synoptic and Dynamic Study of the depressions affected the wider area of Cyprus during the cold season from the same school as above, and a Magister degree from the MBA Program of the School of Management and Economics of the University of Cyprus. He was awarded with scholarships from the Government of Cyprus for Applied Meteorology and Weather Forecast, a UK Meteorological Office College, the US Government Fulbright Commission for Advanced Technology and Remote Sensing, EEC Enterprise Radar Manufacturer, Alabama, USA, National Center for Atmospheric Research, Boulder, Colorado, USA, University of North Dakota, USA, the Government of Cyprus for Advanced Weather Forecast, UK Meteorological Office, and the University of Cyprus and the School of Management. He has published 40 papers on synoptic meteorology and synoptic climatology regarding mainly severe weather over the area of Cyprus, while he attended more than 20 technical trainings, a great majority of them on remote sensing and applications such as radar meteorology, satellite meteorology, automatic weather stations. He has a substantial number of presentations to seminars, workshops, conferences regarding severe weather and the synoptic meteorology and climatology of the area of Cyprus, while he was involved with several European Union and INERRREG scientific programs such as FLASH, BERTIS, MEDEA, etc. He is at the present the permanent representative of Cyprus to the World Meteorological Organization and to several European organizations such as EUMETNET and ECoMet. Dr. Nicolaides, the stage is yours now. You may start with your presentation.
Can you see my presentation?
Not yet.
Not yet.
Not yet. Okay. Let me see. You know, we have checked it earlier, but all things are not happening as we would like.
Now we can see it, yes.
Can you see it now?
Yes.
Yes. So, hello to everybody.
If you could just put it on full screen before you start.
On full screen, yes, of course.
Thank you.
So, dear participants, academians, professors, researchers, students, and all the participants in this teleseminar, thank you very much for the invitation. Thank you very much for being with you today. And thanks to ERATOSTHENES Centre of Excellence and the invitation I received a few days ago for this talk on the science of meteorology and remote sensing applications. After this very short introduction, presentation by introducing the Department of Meteorology. It's only one slide. So the Department of Meteorology is in the organization structure of the Ministry of Agriculture, Rural Development and Environment. It is the official authority of Cyprus, of the Government of Cyprus, for the study of the weather and climate over the area of Cyprus. And by the word study, we don't actually mean academic or research study. It's only operational study of the weather. And since there's a vast number of data since 1900 available, these data are open to the academic community for research and further study. The Department of Meteorology is the member of the World Meteorological Organization, and of course a member of the very essential European organizations regarding the national hydrometeorological services of Europe, those of ECOMET, which is dealing with data sharing, and those of EUMETNET, and that of EUMETNET, which is dealing with technical issues and scientific programs within the European Community of National Hydrometeorological Services. Department of Meteorology is certified by the National Supervisory Authority of Cyprus as an air navigation service provider, certified by the National Supervisory Authority. So the Department of Meteorology, of course, is certified by the Cyprus Certifying Organization with the Quality Assurance Standard ISO 9001-2015. So remote sensing, I'm sure that you know better than me since you are working on this platform of remote sensing at an academic and research level. But let me put a small brick to your knowledge. Remote sensing, according to NOAA, is a science of obtaining information about objects or areas from a distance, typically from aircraft or satellites. So when we have the sun emits its solar radiation towards the Earth or the environment. That solar radiation is reflected, refracted, diffracted, and coming back to the satellite. And the satellite can take images of what the going radiation to the satellite is. Can take a fingerprint of what is in between the emitted and the received radiation. But to do that, you need sensors. Sensors are either passive or active. Passive sensors respond to an external stimuli, like the slide before. The sun is the external stimuli. They record natural and reflected or emitted from the object or the area under the emitter. And these are the passive sensors. And this is the idea behind the first remote sensing development, which was the satellite pictures, why the most freely available emitter was the sun, and the radiation from the sun towards the Earth could result in a passive remote sensing from a satellite. On the other hand, we have the active sensors, which are using an internal stimuli. They produce energy. They send the energy to the environment. The energy towards the environment is coming back, let's say, is reflected, coming towards the receiver, and the receiver can take that fingerprint, what is between the emitter and the receiver. So at the left hand side of the screen, you can see something which is very, very common to meteorologists, is the Earth's energy budget. The sun, it is the source which results to all meteorological phenomena happening in the atmosphere of the Earth, in the troposphere actually, the lower part of the atmosphere. So this incoming radiation is either reflected by the atmosphere, or by the clouds, or by the Earth's surface, or by the oceans, but it is modified and it is going to the outer space again as radiated from the Earth, re-radiated from the Earth. And this is the main concept on which the first passive sensors were constructed. On the right-hand side, you could see a satellite picture as a result of what I said earlier, from the area of Europe, Central and Western Europe, and the Atlantic, showing clouds. This radiation, either incoming or as resulted from the various physical processes within the atmosphere or the air, the sea, is a spectrum of of different wavelengths. Satellites on board, radiometers on board, can measure radiation of different wavelengths and construct images of the Earth, surface and atmosphere for different purposes. So the satellite images was initially either infrared or visible, taking advantage of the infrared part of the spectrum or the visible part of the spectrum of the satellite. Both of them are passive receivers, passing satellite images. The sensor is passive. The infrared is what we call in meteorology a thermal mapping of what the satellite sees below, and the visible is what the eyes see below. It's only a picture, a photographic picture. On the right-hand side of the presentation, you can see the shift of the two spectrums, the visible and the infrared, as a result of the processes happening over the area of the atmosphere or the Earth's surface or the oceans. But satellite imagery is not only infrared and visible. Nowadays, different wavelengths a lot of different wavelengths are employed in order to add value to satellite products for relevant application. The incoming sun radiation needs to be, from the other side, the infrared sun radiation needs to be calibrated. So a variety of passive sensors are employed to calibrate the incoming radiation. So to calibrate the direct sunlight, the diffuse, the infrared, the ultraviolet, the photosynthetic radiation. So these kind of sensors are employed by the science of meteorology, which these are also passive sensors, to calibrate what the satellite sees on the surface of the Earth. And pay attention on what I show you on the left-hand side of the presentation. There's so many satellites which are advancing certain wavelengths in order to produce products for certain applications. These are two typical satellite pictures, the infrared and the visible mapping of the same area at the same time. See the differences. The combination of infrared and visible imagery for the same time can result in very useful conclusions on the coverage of cloud and the type of cloud of an area. The visible can show the cloud coverage, while the infrared, which is the thermal mapping of what is beneath, can show cloud tops and cloud of vertical extent. So the combination of these two pictures can give very, very useful results to the science of meteorology. And if we convey what we say to the channel of the water vapor satellite pictures, in that very small window of the satellite imagery, we can take very, very good results on what is happening on the medium and upper level of the atmosphere, where the jet stream is, where the different curves are existing, and how the weather is going to develop in the near future. Meteorology, of course, is a science, but such a science, as all, needs frequent data. It has the need for frequent data availability. The need for this data are driven from the modern numerical weather products and the software which is resulting into these products. These softwares, these models, these weather models are very demanding in all sorts of meteorological data and parameters. Also, the frequent data are needed for air navigation safety, which is these two areas of meteorology are very, very demanding, and it is much more demanding and higher, this demand of data, since the previous recent years' demand. Data from continental areas, such as surface data of wind, temperature, humidity, radiation, cloud cover, type of weather, soil data from various depths, temperature, humidity, and so on, data from the ocean, such as sea surface temperature, wind, salinity, wave direction, height, subsurface data from various depths, data from various levels of the troposphere, such as wind, temperature, humidity, or from the tropopause and the troposphere, are very, very demanded nowadays from the science of meteorology, and especially from these modern weather models who have such strong needs. In some special cases, such as aerodromes, data must be very, very detailed, spatially and temporarily, for air navigation safety and security reasons. The very sensitive, such as takeoff and land processes of a journey need very, very detailed data, such as wind speed and direction, visibility, state of the runway, whether it is wet, dry, flooded, icy, snowy, cloud cover, amount and height of lower layer clouds, weather phenomena and their effect to the above. This data must be provided at a simultaneous time to the control tower or to the pilot. There are cases where these data are conveyed at near real time to the cockpit of the airplane for decision-making of the captain. What is in use in such cases by the Department of Meteorology? Department of Meteorology receives data from different sources of remote sensing, such as passive remote sensors, such as satellite imagery, which was discussed earlier, active remote sensors, such as radar, runway visual range, height of cloud base, HCB, dysdrometer, automatic weather stations network. These are the sources we today at the Department of Meteorology receive data from sensors such as remote ones. Let us examine first the radar, the radio detection and ranging active sensor, the well-known radar. The surveillance of the surrounding environment, targeting on weather and weather impact, is of very much significance and great interest for operational meteorology. Also for data use for academic purpose. A lot of study and research can be found within the radar volume scans. The traditional method for weather surveillance, which was by observation from personnel in meteorological stations, is not valid today. We need to know the energy at every point of the surface of the Earth and at every point in the troposphere. So personnel is limited. The efforts of personnel is very limited to produce observations at every point of the environment. Radar is something which is doing that purpose and in very, very good manner. The contribution of radar technology is very positive towards weather surveillance by emitting a pulse of certain frequency and amplitude towards the space, towards the environments, receives back a fingerprint, an echo of the space from the beam, from the area from where the beam has passed through. And of course, don't think that the beam is so wide. The beam is only 1 degree by 1 degree only, but the surveillance is examined by elevating the antenna after a full scan by some degrees. So at 0 degrees, a scan. At 1 degree, another one. At 5 degrees, another one. At 10 degrees, and so on and so forth. And the resulted scan is called a volume scan. To calibrate the radars, we first have to find the coefficients and the parameters of the radar's reflectivity equation. This is a process which needs statistics, at the field experiment, rain gauges, dysdrometers, and so on and so forth. These characteristics are characterizing the area where the radar is and the climate in which the area in which the radar is operating. I have to say that meteorological radars have three let's say bands. We are using in the globe 3 bands of frequencies in order to characterize the radars. The S band, which is huge antennas with great powers, so great they can detect hurricanes, tornadoes, large hail. We see them in the main plain areas of the states, in Siberia, in extensive areas where they see, let's say, something like 500 kilometers away. So mainly in huge plain areas or in the tropics. The C-band radars, which can be more useful where there's a signal attenuation is likely to happen due to the general climate of the area. The area of Cyprus is an area where C-band can operate. They can see far away, again, depending on the height they are installed. And the third group is the X-band radars, which are the radars with shorter range, suitable for meteorological or hydrological applications in small areas like big towns or valleys, close areas. The Department of Meteorology employs services from a network of 2 X-band radar installed over the area of Cyprus, one at Nata, at Paphos area, and the other one at Rizouelia, at Larnaca area, the combination of which is giving us very, very good results on the weather advancing over the area of Cyprus. Of course, these radars have a small diameter of surveillance, something like 150 kilometers, but they are very, very useful to the operational meteorology of Cyprus. This is a picture of the old C-band weather radar installed at Kikos Mountain, and at the lower right part is an echo of a severe hailstorm. You can see the height of the cloud, 32,000 feet, 32,000 feet, and the dense and the red color at the center, at the core of the cloud is the hailstorm. These are the 2 X-band radars, their positions, Nata and Rizouelia, and the area which they are covering. And you can see now images from our application of the 27th of November. You can see the storms advancing over the area of Cyprus. These storms resulted in extreme weather over the south part of Nicosia. You can also see the height of the cloud at the graphics to the top, or a cross-section at the graphic to the right. You can also see another at May last year, the 5th of May, which resulted in a flood over Nicosia, the eastern part of Nicosia suburbs. When we talk in our weather forecast about local thunderstorms, this is what we mean. That is a local thunderstorm. That is a local thunderstorm. The width of this thunderstorm is not more than 3 to 4 kilometers. And this is what we need the public to know. Local phenomena are very local phenomena. And see now, of the same date, the cross section of the cloud, the hail in the cloud, the different kind of reflections. These reflect to hailstorm. The red and the purple one result into heavy precipitation and or hailstorm. And this is the cloud as seen from an eye, a visible picture, and this is the hail resulted from the hailstorm of the 5th of May, almost 1 centimeter of diameter, very frequent as a hail diameter in Cyprus. And you have to know that hail in Cyprus is frequent during the transition seasons from winter to summer, or from summer to winter, or when we have very, very active fronts advancing the area of Cyprus. But we do perform some applications, special applications, in the framework of the bilateral collaboration of the Department of Meteorology of Cyprus and Israel. Data from rain gauges and low-level radar data from volume scans are assimilated, have been assimilated into COSMO model. COSMO model is a Deutsche Wetterdienst limited area model of the German meteorological department, of this limited area model for calibration. And the calibrated numerical weather products for COSMO are then received by the Department of Meteorology for applications. We see that different kinds of graphics are coming to us, cross-section of cloud, with respect to time, precipitation. These blue bars are for the advancing precipitation, temperature, wind field, temperature of the troposphere, and so, and of course, temperature at various levels. There are also some more special radar applications in the so-called OPERA. OPERA is a special program of EUMETNET. Remember, I talked to you earlier about EUMETNET. The need for a better knowledge for the developing, advancing weather over Europe. This has driven the need of OPERA program. OPERA produces a mosaic of most of the EU countries members to EUMETNET radar products. So the OPERA mosaic is very useful, mostly to the European Centre of ECMWF, European Centre for Medium Range Weather Forecast, while it is giving a snapshot of the developing and the emerging weather over the area of Europe. Cyprus would be very happy to support OPERA with radar data, but there's always a but. Cyprus is not a member of ECMWF, but is a member of EUMETNET. Turkey, our neighbor, is a member to ECMWF, but not a member to EUMETNET. So application of Cyprus to be part of ECMWF, application of Cyprus to get into ECMWF as a full member falls due to Turkey's veto. So due to these reasons, at this time, it is impossible to convey radar data to OPERA. This is a recent image of OPERA mosaic. We see the fronts in the area of the Central and Western Europe. The light shed over the area of Europe is the coverage of the radars. So at certain times every day, all OPERA members send data to ECMWF. ECMWF is creating this snapshot, and according to this snapshot, experimentally, the NWP produced earlier by ECMWF are corrected. Let us see more applications. Runway visual range, an active sensor, while landing or taking off, which are the most sensitive parts of flight operations. The horizontal visibility along the runway is very crucial. The captain on board needs very detailed information on the variety of on the variations of AVIA for decision-making purposes, land or abort landing. Why? Air carriers have limitations. You can land with this horizontal visibility, you cannot land with less. During the last 40 years, the RVR system was developed and adopted, and transmitter emits a wave of energy. We can see it in this screen. A transmitter transmits a wave towards the receiver. The receiver and the transmitter are apart either 5 or 50 meters. So what is coming to the transmitter is a fingerprint of the pocket of air in this area, in between them. These two sensors are just by the runway, So it's a very good approximation on what is happening on the runway this aeroplane is going to land. And this is our RVR graphic. You can see that at the level of 2,000, at the distance of 2,000 meters, where RVR is more than 2,000 meters, the RVR is not resulting to anything. But when the visibility gets lower from 2,000 meters, then it starts measuring and giving results to our observers, and our observers convey all these informations to the control tower for any action on the advancing airplane. You see that there are measurements of 100 meters. There was a fog situation on July 15, 2008. Doesn't matter the old of this case. It is not only fog resulting into the reduction of the visibility. It's also dust, precipitation, which is resulting into limitations in the visibility. But as RVR, it's also the HCB, the height of cloud base, also an active sensor. Again, when landing, the cloud cover and the distance and the above ground level base must be in certain criteria must be applied. When the cloud of base is less than 300 feet and the coverage is more than 4 octas, then certain air carriers introduce restrictions in landing. The captain on board needs very detailed information. So HCB, which is an emitter, emit a beam towards the sky. The beam is reflected to the receiver, both transmitter and receiver at the side of the runway, and they result in this graphic. We know the velocity of light. We know the time between the emission and the reception, so we can take results for the cloud base. In this graphic, 2 layers of cloud exist at the same time. The one having base at 5,600 feet, and the other one with variable bases from, let's say, 1,600 to 4,000 feet. And these data are again conveyed to the control tower or directly from the control tower to the captain for decision making. Dystrometer. The measurement of the geometrical characteristics of the raindrop is very essential for meteorological and hydrological purposes. Dystrometer or rain spectrometer is a laser instrument which is also active because it produces the energy in our case. It may be also acoustic, so it's a passive. So dystrometer can measure the drops and the size of the distribution of the raindrops of all falling hydrometeors. Based on the principle of optical laser active detection, the dystrometer can continuously observe the raindrop size and quantity. There are these 2 kinds, the acoustic and the optical. The principle is very easy. A known energy pulse is sent from the emitter to the receiver. This known energy results in a 5 volts voltage in the receiver. Any hydrometeors, snow or raindrop or hail or anything passing through this free space results in the reduction of the voltage created into the receiver. And it results to the distribution of the velocity and the diameter of the raindrop. Very useful information can be picked up from this distribution during a rain event. The most obvious is that the greater velocity to greater diameter raindrops, which means that in a multi-layer cloud cover where different types of different size of drops fall, the disdrometer can say, you know, you have a layer cloud at the bottom, but aloft there's a vertical extent cloud with great vertical extent, with results to heavier and with greater velocities drops. Of course, the Department of Meteorology employs for the convey of our measurements throughout Cyprus. All these black dots over Cyprus are our automatic weather stations, which measure, and all measurements are conveyed by the 2 or 3 or 4G network of the telecommunication authority to our database. So at any time, we know what the temperature is, what the wind is, if it rained, how much it rained, what's the relative humidity at a certain station at a certain time, and so on and so forth. So we have a snapshot of what is happening around Cyprus at any time. A few things about what we see in meteorology, the future of remote sensing. I think that without any doubt, it is the future. Since all the models, the weather models around the world are so demanding in data, the only solution is to apply to remote sensing, because they can support a variety of applications, because they are reliable, because they measure continuously, because data from everywhere can be accessible. There are no hidden areas or remote areas. The data acquisition problem in that way has another possible solution. And of course, the academic research finds another fit for exploration. I came to the end of this presentation. I think that I am on time. For that, I would like to thank you very much and for your participation. And I'm here to respond to your questions. Thank you very much.
Thank you, Dr. Nicolaides. We will go back to Professor.
Can you hear me?
Before the questions. I think now it's better with the microphone.
Okay. I would just like to thank you for the very enlightening presentation. You covered a lot of ground, and it was definitely something that we can build upon. And as the ERATOSTHENES team would like to strengthen the collaboration with the Department of Meteorology, which has already been at a very good level, also with the legacy of Silas Michailidis before. And we are looking forward to making essentially a big steps in terms of contributing to the mission in the region and beyond. Thank you very, very much for your presentation. Eleni, can you take over now? Thank you.
Thank you. We can go on with the questions. We already have one question. In which stations, areas are the disdrometers available?
Disdrometers are available at the 2 airports and also at Athalassa station, which is that one I show you is a property of the Cyprus University of Technology. And we are planning to implement results from that disdrometer into a scientific program, a proposed one. You know, to see what things, what are the things happening at the surface of the Earth when you apply technologies from the space you need something very reliable at the surface of the Earth. Let's take into account the TRIM project. TRIM project was a project 15 years ago, which was measuring from a radar on a satellite. There were scans were performed towards the surface of the Earth for the precipitation, but you had to correct that scans at the surface. A distrometer is an idea. The rain gauge is another idea. So distrometers, to your initial question, are engaged at the two airports and at the Thalassa station.
Thank you. Does the Department of Meteorology own a passive sensor network for radiation calibration?
Yes, of course. We do have installed at Thalassa. It's a main one measuring all solar radiation parameters. And there are also at the coast area of Cyprus, at Polis Chrysochous, at Larnaca, and at Paphos. At Paphos, at Troodos station. You know, these sensors, not that it is so expensive, but there's a limitation to maintain our network. So we have set up quite a few of them at the areas I have told you. Our will is to put as much as more to result in the various applications are needed today from the society.
And another question, have you done studies for the different stratosphere profiles during a year for the southeastern Mediterranean region?
The only data we have from the lowest stratosphere, or I would say from the troposphere, from the tropopause, is the radiosonde data, which is performed twice per day. That is another remote sensing technology, which I haven't said earlier. By this means, we release at the atmosphere a sensor which is measuring all weather parameters I said to you earlier, except that of the radiation. And the data are coming towards the Earth through a satellite. So this small sensor is engaged by satellites, and these satellites receive the messages from the sensor, temperature 1,000 feet, so wind speed and direction, so and so on and so forth at the next level and next level and next level, and they are transmitted real time towards the Earth. This is going up to 160,000 feet, so it is in the tropopause or the very low stratosphere. These are all the data we have.
And is radar data available for research purposes?
Radar data and all the data of owned to the Department of Meteorology are free for research, and we welcome academic organizations for our mutual benefit to examine and make research on this data. TEPAC, the Technical University of Cyprus, through Eratosthenes, used for quite a lot of times such data. And we are very happy on that. And as Professor Kyriakidis said, research is not only for the sake of research, but for mutual benefit. So data are there, we can use them.
Thank you. I also have a question on radar data. Actually, do you use any satellite data to compare the radar measurements, or do you only calibrate them with the in situ data?
The in situ data are produced from the rain gauges. So what the rain gauge within the radar volume scan resulted in precipitation can be compared to the data, to the radar data. These are a part of the research. The Department of Meteorology has limited sources, very, very limited sources. This is the reason we collaborate with academians, with the BAC and other academic organizations to give solutions to our problems. And this is a problem. Reflectivity, let's say, says that the rainfall rate is such. Is it such? From where are we going to take it? From the rain gauge. So this is a place academic organizations can take part.
Thank you. And how feasible is a crowd data acquisition, installing feed sensors on publicly owned properties such as boats, cars, etc., to facilitate broader microdata acquisition?
Let me rephrase this question because I'm also interested in that. I know that several departments might take measurements of, they have sensors, and in the sensors or next to them, they might measuring parameters that you are also measuring. I understand that you have a mission, and that mission is through your own instruments, and enough headache is to one's head for maintaining all those. So I guess the question might be, how can we make those interoperable? How can we use other data that might come from other sources? And whether the Meteorology Department, the Department of Meteorology, has done something on that, or is interested in this, or what is the position on that? Or is it, we have enough, we don't have enough time to manage our own things, don't let us speak about other things. So where is the middle ground? I'm sure there are many people that are interested in this question. There are many, many sensors out there. They measure different things with different accuracies. And there is a problem of research, problem of data fusion, of interoperability, things like that. Thank you.
Let me put something which was presented in the 18th Congress of World Meteorological Organization last year. The Secretary General showed us his mobile, which has a barometer sensor. So everyone, when setting up his mobile, if he allows the factory to have access to its data, i.e. the barometer data, can at the same time draw an isobaric map at a certain time worldwide. So, in that respect, data are always requested, and data are outside in huge amount. In Cyprus, we do not have a law on meteorology. And this is limiting our efforts. I would like to, we would like at the Department of Meteorology to apply to the General Attorney's Office for a law on the applications of meteorology, concerning meteorology. And all these data, it would have then not being a property of the department, but could be used by the department when they obey to a certain protocol. It's the collaboration between national hydrometeorological services and private organizations or privates is very essential for the WMO, the World Meteorological Organization, today. And if we take into account the freely access of data, of high value data, and meteorology has high value data to the community, then somebody can understand why your question is so of great interest. It is my strong belief that we have to go towards a law to make a chart of our rights and responsibility. Private organizations, government organizations, and so on.
Great, thank you. I think I will give some more seconds for some last questions, if there are any. Yeah, another question. So to our understanding, the data and the ground truthing are very valuable information, especially for the region with unique positioning such as Cyprus. Is that right?
Can you repeat the question?
To our understanding, the data and the ground truthing are very valuable information, especially for the region with unique positioning as Cyprus. Is that right?
It is right, of course. And if I can add, not only for the continental area of Cyprus, but data from the sea surrounding Cyprus, let's say the exclusive economic zone or the sea area of Cyprus, we are trying to introduce but to install sensors on ships moving into our exclusive economic zone, but our sources are so limited, we cannot do that. It's not really a good thing to know what is happening over the continental area, but having no idea of what is happening around. So data in that respect, as Professor Kyriakidis said, are so useful for all. I'm sure that many ships on board have barometers and wind speed and direction sensors and temperatures, and sea surface temperature meters and so on and so forth. But I don't have accessibility on those data as a department.
Thank you. And one question from Professor Hadjimitsis. Maybe we can also close after answering this question. How the meteorology department will support the EXCELSIOR Horizon 2020 teaming project and ERATOSTHENES Centre of Excellence?
Thank you very much for the question. It's from the early days of ERATOSTHENES Centre of Excellence and through the teaming Horizon project, which is meteorology support these efforts of the BAC, of the University of Technology, not only through our knowledge, but also by providing data and providing our technical expertise on issues of our, let's say, responsibility. We are here to help for the mutual benefit by improving the efforts of the BAC. The benefit is not only for the BAC, it's for all our society, for Cyprus, and this is a reason we are fighting for.
Great. Thank you again, Dr. Nicolaides, for being with us today for the presentation and also for the great discussion after the presentation. Thank you to everyone who joined us today. And with this, I think I can also wish you happy holidays and healthy holidays. And see you next year. Goodbye. Thank you.
Thank you very much, and happy holidays to everybody. Thank you very much.
Thank you. Bye-bye.